All right, now we are going to look at the graph part. Okay, in graph, firstly let us look at state. What is state, or the shared state is nothing but it's like the memory that gets shared across all the different nodes in LangGraph. Okay, so we're going to define the shared state that flows through the entire agent graph, and every agent is going to read from and write to this particular state object. Okay, so here you can see we have created two classes, like two state objects. One is signal output, which is type dict, okay, and one signal generated by specialist agent. So it is going to contain, these are the fields, okay, that are going to shared across all the agentic nodes, which is agent, signal type, which means it's a broken promise, missing results, all of that. If you can recall, if you look at the agents, these are all looking at different signals: NCT ID, summary, evidence, and confidence, okay, which is from 0 to 1. Then again, if you see class mosaic state, now this is the complete state that gets shared across all the nodes in the mosaic graph, which is typically type dictionary, right? And LangGraph passes this state between the nodes automatically, and each and every agent receives the full state, does it works, and returns only the fields that are updated, which means it receives a full state and gives a partially updated state. Okay, so at that what are the things it will take? So at the task input level, it is going to take the task, which is the analysis task description. It is going to take the NCT IDs, which is the list of strings, maximum number of studies. Then the conversation history, which is the messages. Okay, now annotated, we're going to use annotated with add messages. It tells LangGraph to append new messages to the list rather than replacing it entirely. So these are messages. They can be tool messages, human messages, AI messages, system messages, all of that. Then agent outputs, signals. What are signals? Basically, they are the outputs given by all the agents. We're going to store them as a list of signal outputs and which agents are activated, which means which agents have run. Then what are the supervisor outputs? Now we're going to have one supervisor agent. Now you can just go back to our diagram. From our diagram, you can see we are using one supervisor agent, right? And supervisor agent is just going to look after all the other agents, right? It is sub-agentic in nature. It is not doing a task. It is just going to kind of delegate the task to different agents, right? So our supervisor outputs are going to be two. One is the final brief, which is the entire compiled intelligent brief, and whether the run is complete, yes or no. It is just going to check if that particular agent has run or not. Okay, and the metadata. And metadata for each run, we're going to have a unique ID, which is run ID, and the error log, which is a list. Now these are typical fields, yeah, that are going to be shared across the entire schema, which will be getting updated. Okay, next is basically graph builder. Okay, and this is where we build our entire, or bring all our things together. Okay, now as of now you can see here, okay, what does the graph builder do? It is going to wire all our agents. Now as of now we have not defined the agents, but we're going to just define the graph builder. We're going to build it and keep it. Okay, it is going to take all the agents and it is going to build or wind all the agents here. Okay, and this is how the graph structure looks like. It will start, then it will go to the supervisor route, which means on starting it will go to the supervisor route. Then supervisor route is going to decide which agent it will run. Basis the query given by the user, it is going to run that particular agent, and all 6 specialists, you can see they're all running in parallel. Yes, and once the output that you get, once the output is generated, okay, supervisor is going to compile, which means it is going to read all the signals. Whatever signal is generated by the output, it is going to be recompiled by the supervisor agent and is finally going to end. Yeah, so we're going to from langgraph.graph, we're going to import state graph, start and end. We're also going to use something called as tool node. Okay, then from graph.state, which is, you can see, yeah, state.py, we're going to import mosaic state. Then as of now in agents, these are all different agents and files. As of now we have not imported them, but from agents.supervisor, we're going to import supervisor route and supervisor compile. From broken promises agent, we're going to import broken promises node. From missing results agent, we're going to use missing results node. From track record agent, we're going to use track record node, pattern finder node, side effect agent, side effect node, timeline agent, timeline node. Then we're going to import all the tools that we have defined, all search tools, clinical tools, and PubMed tools. Okay. And let's say if I want to access all the tools. So I'm going to create one variable called as all tools, which is combination of all the tools, which is all search tools plus all clinical tools plus all PubMed tools. I'm going to create a function called as build mosaic graph, which builds and compiles the entire graph at one shot. Okay. What does it return? It returns a compiled LangGraph that is ready to be invoked. Okay. And we call this once at the startup. Okay. All right. Here we're just going to create the graph. So we're going to take the state and we're going to pass it, and state graph basically makes our state type dict. And every node in the graph receives and returns the mosaic state. Yeah. So we're going to take the state, pass it into state graph and create a graph object. Then we're going to take tool node. And what is tool node? If you can recall, we have already imported tool node here. Okay. What is tool node? Tool node is a special LangGraph node that executes tool calls. Okay. When an agent returns a message with tool calls, LangGraph routes this to the node which runs the actual tool functions. So I'm just going to put in this tool calls, or rather all tools in tool node. I'm going to call this as tool node. Okay. Now in the graph, I'm just going to add all the nodes. Okay. So I'm going to add the supervisor route. These are different nodes and these are different functions. Okay. Supervisor route, broken promises, missing results, track record, pattern finder, same side effect, timeline, tools and supervisor compile. We're going to add all these nodes to our graph. Okay, graph nodes are basically like individual tasks that your agent is going to perform, or your agentic workflow is going to perform. You can see here when we're going to add a tools node, it is going to use the tool node that we have defined here, which is going to access all the tools. Yeah. We're going to log it. Okay. And then let us define the edge. So you can see we're going to start, then we start with the supervisor route. We know that all our agents are going to run in parallel. So we're going to add the edge from supervisor to broken promises, supervisor to missing records. Basically, if you see supervisor to broken promises, supervisor to missing results, supervisor to track record, supervisor to pattern finder, supervisor to side effect, supervisor to timeline. Timeline, correct. So we're going to add all the connections in between. What are these connections? Connections are basically edges. Edges basically decide or determine which nodes it should run. Okay. Then we are going to basically compile all the specialists. So after all the specialists finish, supervisor compile runs. It reads all the signals from the state and writes a final brief. Okay. So we're going to add an edge back from broken promises to which means the output of each and every agent will go back to the supervisor compile. Now if you see here, we are connecting from supervisor to broken promises. Then whatever output is given by that broken promises, that will go to supervisor compile. And what the supervisor compile is going to do, it is going to compile all the results from each and every agent. It is going to generate an output or a brief. And you can see here, and then from supervisor compile, we're going to end the entire graphical workflow. We're going to compile the graph. We're going to compile this in a compiled object. We're going to log it, and what do we return? We return the compiled object here. Okay. And finally, what do? We build the graph once at the module import time. All the API requests share this single graph instance. So if you see here, we are just calling this build mosaic graph, and we are storing this in an instance called as mosaic graph, and all our API requests will be using this. So we have defined the state, we have compiled all the agents and all the nodes and defined all the edges in the graph builder. And the last part in the graph pipeline, or the graph part, is human in the loop. Okay, which is super important, right? So when an agent's confidence is below its threshold, the signal goes into the review queue instead of being saved directly. If you see here, when we are looking at human in the loop, yeah, it will look for confidence levels, and if that confidence level is below the threshold, only then, which means the confidence level of the output or the signal that is generated, is below a certain threshold, only then will it go in the review queue, and that is where the human in the loop will be applied. Okay, a human analyst reviews it, approves it, rejects it, or edits it. And you can recall this rejection directly impacts your procedural memory, right? Whatever gets impacted here, if you see here, I've defined here learning loop, and it is going back and hitting your procedural memory. You can see here. Yeah. Now, rejections feedback feeds back into the procedural memory, which is the learning loop. The learning loop we have defined here. You can see here, learning loop. Your rejection region is going to feed the procedural store update. A new rule added to the agent, okay, and the agent loads every future session permanently. Okay, we're going to import UUID. From datetime, I'm going to import datetime. Okay, I'm going to import async PG. Then from memory.procedural store, I'm going to import procedural store. Why I'm going to import procedural store? The simple reason being, the feedback given by human in the loop directly updates your procedural store. I'm going to create a logger object, and then I'm going to define confidence thresholds. And you can see I'm defining confidence thresholds per agent. Now, if the output given by that particular agent is below this particular confidence threshold, only then will it go in the review queue and a human in the loop will be applied. Okay, I'm going to define a class called as HITL gate, which routes the signals or the outputs to either direct save or the human review queue based on the agent's confidence score. High confidence, which means saved directly to the signals table. If you can recall, our Cloud SQL has a signals table. Yeah. So if you just go here and if you just again type Cloud SQL and you go to SQL Studio, I've already told you how to go there. All of that. Okay. Now if you just go to the SQL Studio or the Cloud SQL Studio, you can see the Cloud SQL Studio. Okay. You can just connect. And once you connect in the tables, you can see the signals table. Okay. Low confidence means it is going to send to the review queue table for the human in the review. Okay. Let's actually check that here. Which database? Clinical trial DB. I'll just say okay. And now if I just go in here, you can see HITL reviews. This is human in the loop reviews. These are 7 columns that will be populated as per the human decisions, right? Decision, edit, summary, rejection region, all of them. Just how you have HITL, you also have signals. Okay. Signals are the outputs generated by your agents, and the outputs generated by agents are going to populate these 9 tables, which is NCTID, agent, signal, memory, evidence, all of them. Okay. Alright, we're going to create a constructor function. It is going to create an async G pool. I think we have already discussed this, and it is also going to create the shared instance for procedural store. Okay, then we are just going to ensure if the pool connection is available, and when we create the pool connection, these are the settings we take into consideration. Not the settings, sorry, like the variables we take into consideration. Host, port number, which is 5432, database name, user, password, min and max size. Then I'm going to create an async function which processes the signal. Okay, what does it take in an argument level? It takes the signal, which is what? A dictionary. Okay, and gives a dictionary in the output. So it routes one signal through the HITL gate that we have created here, and it returns the dictionary with the key. Which key is action, signal ID, or queue ID. Okay, and the action is either saved directly or sent to review. Okay, so there are only 2 actions: save directly, which is it's saved, or it is sent to review, which means it is in the HITL. It will check if the pool connection is available. Then from the signal, which is the output, it gets 2 things. Okay, one, it takes the agents, what is the name of the agent, and what is the confidence level. Else, if not unable to get the confidence level, it is going to set it to 0. Okay, then from confidence threshold, it is going to get the agent name, and else by default 0.65. Now from this, I'm talking about this confidence threshold, it is going to take the agent name, else by default it is going to set it to 0.65, and that is the threshold. Now if your confidence is greater than the threshold, okay, it is going to save that signal into signal ID. It is going to save that signal, it is going to extract the signal ID. This is the high confidence case. High confidence means save directly to the signals table. So if the output given by your agent is high confidence, it is going to get directly stored in the signals table. It is going to take the signal type, it is going to take the confidence, okay, and it is going to log. Else it will be in the queue, which means it is this helper function will define this helper function, which is send to review queue. It will take the output generated by your agent, which is the signal, and it will apply this helper function, and it will take the queue ID. Okay, it will give you the queue ID, and that will be logged here. Okay, so the action is send to review, and what is the queue ID? It is also going to generate the queue ID. We're going to create one more async function to save the signal, okay, which means it takes the signal and gives a string. Now this inserts a high confidence signal into the signals table, okay. To that signal, now this signal ID is UUID, which is, it has a unique identifier. We're going to create a pool, this standard pool connection. It is going to check, it is going to look at the connection, it is going to execute. Now when do we use .execute? When we want to do CRUD operations. Now here into signals table, we're going to use signal ID, NCT, agent, signal type, summary, all of them. Now if you just go back to signals table, you can see all those tables here. Okay, these tables we want to populate. Okay, so you can see from, we're going to get NCT ID, agent, signal type, summary. If nothing, then just set it to empty, right? And from signal, if you can see json.dump signal.get, we're going to get the evidence, we're going to get the confidence, else 0, and approved, which is high confidence bypass reviews, that the status is approved. So basically in these things, we're going to update all of this. So in status, we're going to set approved. In confidence, now from this confidence, from signal, we're going to get confidence, and whatever confidence we're going to get, we're going to populate here. Then what is the evidence we're going to populate here? All of that gets populated in the signals table. And what do we finally return? A signal ID, which is the UUID. Similarly, we're going to create an async function, which is send to review queue. It takes a signal, which is again dictionary. So it inserts a low confidence signal into HITL reviews. Now, just how your high confidence output will be stored in signals, your low confidence will be stored in HITL reviews. So any data that is in the queue gets stored in this particular table, which is HITL reviews. Okay, where is it? Yeah. Okay, so state, and for this one the status is pending. So in high confidence the status is approved, in low confidence the status is pending, and for obvious reasons, self-explanatory. So we're going to take the queue ID because it will be in the queue, right? We have discussed here, it is going to be in the review queue. Now this individual review will be having a queue ID associated with it, again UUID4, again a signal ID associated with UUID4. Okay, then in that signals, again you can see, again we're going to just populate everything. We're just going to say table, like pending. The only status here is going to be pending, the rest of the things are going to be the same. Okay, then we're again going to insert into HITL reviews. HITL reviews, we're going to populate review ID, signal ID, and decision. Okay, decision by default is set to pending. It is going to populate review ID and signal ID. Okay, then one more async function we're going to create, which is process the human decision. It takes the queue ID, it takes the decision, which is to approve, edit, or reject. It takes the reviewer, rejection region as of now empty, and edit summary as of now empty, and gives dictionary in the output. So it basically processes the human reviewer's decision on the queued signal. Okay, whatever the queued signal is, the low signal output, okay, or the low confidence output, it is going to either approve it, edit it, or reject it. Okay, so signal status becomes rejected, and rejection region is written into the procedural memory, and that is your learning loop, this one. Yeah, all right, we're going to check the connection is open or not. Okay, and in that connection we're just going to fetch a row, just going to run a simple SQL query, which is going to get the signal ID from the HITL reviews where the review is 1, whatever we have defined here. Okay, and if not row, it is going to just return success false, and it is going to give an error. It is going to extract the signal ID and the new status. Okay, so if the decision is approve or edit, okay, then approved, else rejected. Okay, all right, it is going to update the signal status. So update the status, but it is going to just update the signal status. Yeah, 2 fields are getting updated, new status and signal ID. Okay, then we update the review record with the decision. So our HITL requires an update also, right? So HITL reviews will also get updated. It is going to set the decision to this, reviewer to this, rejection region to this, edit summary to this. These are just placeholders. So my decision is at placeholder 1, reviewer at place number 2, etc., etc. Okay. If the decision is to edit and the edit summary, then I'm going to update that accordingly in the table. Okay. Then comes the learning loop, which is the most important part of human in the loop. If the human rejected the signal, then write this to the procedural memory so that the agent reasons differently next time. Which means if the decision is to reject and takes the rejection reason, then it is going to take the gets agent for, it is going to take the signal ID, it is going to apply this function, it is going to fill up the agent row. If the agent row, then it is going to, from the procedural store, update from feedback, it is going to take the agent name, which is the row, and the rejection region. Okay, so you can see it is going to take this basis that it is going to update it in the procedural store. Okay, it is going to log that the procedural store memory has been updated from the rejection, and it is also given the agent row. Okay, and what is this agent row is nothing but the agent name basically. Okay, and what does it return? It returns success as true, decision, signal ID, and the queue ID. Okay, and these async functions that we are defining, which is get agent for signal, okay, get review queue, all of them I have defined them here. And finally, what do? We close the function. We close the, not the function, we close the pool connection, the database connection, once we are done interacting with it. Okay, in this function, what we are doing, we are taking the signal ID and it returns the agent's name for the given signal ID. That's all. You can see, select the agent from signals where the signal ID is placeholder. We already defined this placeholder values. Okay, and get the review queue. What does this do? It returns all the signals currently pending from the human review, which are all the outputs that are currently pending, or current signals, which is the agent outputs, which are currently pending on the human review level. All of that is getting updated in the human, in the HITL reviews. Okay, here we have just applied a simple inner join. Okay, with so here we have actually applied an inner join between the HITL reviews and the signals table. Okay, and we're just going to look at all the records where the decision is pending. So this query gets updated. Okay, and basis this query runs in this particular function. That is how we get to understand which signals are pending for the human review. As simple as that, guys. That forms your graph pipeline with state, graph builder, and human in the loop. Okay, all right, now let's go to the next part and let us build agents one after the other. Yeah, thank you.